Welcome to Maths for All. I'm Aisling Flynn and this is Higher Level. This is Functions, Quadratic Functions. So we're going to start by graphing some quadratic functions. Graph the function f of x equals x squared. So it is this squared term here that makes a function quadratic. Okay. The word quadrat means square, quite literally. Okay, so in the domain from -4 to +4 where x is a real number, okay, and we can do it by working out the table for all the inputs and getting the corresponding outputs. Okay, so if you look at the first one there, x squared is gotten when you take your input -4 and you square it, it becomes +16. Okay, that's important. -4 by -4, so negative by negative gives a positive, and in fact anything squared will give a positive because you're multiplying two of the same type. Notice that the output for +4 is the same. Okay, and if you look closely you see that there is a pattern. We have decreasing outputs 16, 9, 4, 1, and then to 0. Okay, and then it's increasing to 1 for the reverse of that, 9 and 16. Okay, let's see what that looks like on a graph. Remember, you can generate this table, these outputs, using your calculator. We've seen how to do that with linear functions, so it's just the same. Select alpha to select right or red writing. Okay, type in your x and then press the square function to give you x squared. So give that a go and see, do you get the same outputs? So let's put this on a graph. And this is what it looks like. So we have our inputs x along the horizontal, and we're asked to go from in the domain -4 up to +4. Okay, and f of x, or our outputs, is on the vertical axis or the y-axis, and that was our first point there, -4, 16. Second one was -3, 9, -2, 4, -1, 1, and we had 0, 0. Okay, and then we went up the other side. So +1 also gave 1 as an output, +2 gave +4, +3 gave +9, and +4 gave +16 also. So what results is this nice U shape, okay, and it is symmetrical, same left and right. So the graph is of a symmetrical nature, so the left is the same as the right hand side. The vertex of the function is at 0, 0. So 0, 0 is down there at the bottom. Okay, the red arrows pointing to it. This may also be called the minimum of the function. Okay, so minimum meaning the bottom or the lowest value is at 0, 0, and it can be called the turning point because before 0 we have a decreasing function. Okay, so everything is going down, it's decreasing, and then it turns at 0, 0 and becomes an increasing function. It's climbing or rising. Okay, where does this graph cut the x-axis? So where does it cut, or in this case it just touches? Okay, the x-axis. Well, it is at that turning point. It touches the x-axis at x equals 0. And this function has two identical roots at x equals 0. Now what does that mean? We had root for the linear functions, and it was where the function touches or crosses the x-axis. Okay, here the root can be seen at x equals 0, but in actual fact there's two roots, and let me show you how you would get that algebraically. Well, our function was x squared, okay? When is the function equal to 0? So you would get x is equal to square root of 0. So x would be plus or minus 0, which is the same thing. But the important thing is you'd have two values. Okay, for a quadratic equation, you always get two values. You'll see this in further examples more clearly. Where does the graph cut the y-axis? Well, it crosses the y-axis at y equals 0 also. Okay, again, in further examples, we'll see how that differs. The y-intercept is equal to 0. Okay, so let's try a slightly different one. This time the function f of x is x squared plus 1, so a little bit different. There's the extra plus 1 there. Same domain. And here's the table. Now let's look at the results, the outputs. Okay, so the input is minus 4, so we have to square it. Remember from the previous table that was plus 16, and 16 plus 1 is 17. And before we had 9 plus 1 is 10. And we had 4 before, 4 plus 1 is 5, and so on. Okay, so everything is 1 larger than before. Okay, again, you can use your calculator to generate those outputs. Okay, so what does that look like on a graph? Well, it looks very, very similar. There's that nice U shape, symmetrical left and right. Okay, and there's our points plotted. So the graph is of a symmetrical nature, or it is symmetrical. Now, this time our vertex, or turning point, is at 0, 1. So x value 0, y value 1. And this is also called the minimum, or the turning point. Okay, and you see that every point is 1 higher than before. And it has the effect that the whole function is shifted up the page by 1 unit. Where does the graph cut the x-axis? Well, it doesn't at all. Okay, this function has no real roots. Okay, so let me just show you. You've met no real roots, as in imaginary roots, before when you did complex numbers. Okay, so let's see how we get that algebraically. Okay, so this time our function is x squared plus 1. And when is it equal to 0? Okay, so if you're solving for x, you could do x squared equals to minus 1. Now there's your clue, negative 1. And x would be a square root of a negative 1. Now in complex numbers we learned that that's not possible for real numbers. So therefore we have no real roots. This one, we learned that the square root of minus 1 is I, so x is equal to plus or minus I. Okay, so there's no real roots. We cannot see them on the graph. The function does not cross over the x-axis. Where does the graph cut the y-axis? And it crosses the y-axis at 1. So your function was x squared plus 1. So the y-axis, every point up along the y-axis has an x value of 0. So what's 0 squared plus 1? Well, it's 1. That's how you get your y value, your y-intercept. The y-intercept is 1. The graph seems to have shifted 1 unit up, okay, from the previous one. So the effect of adding on that extra 1 seems to have shifted the whole function up by 1. Okay, now let's try this one. So it's quite similar again. We're starting with x squared, but f of x equals x squared minus 3. So there's the domain, and there's the table. Again, use your calculator to generate. Okay, remember that x squared, when the input was minus 4 was 16, and 16 minus 3 gives me this 13, and so on. So all the values are 3 less than the original table. Okay, what does that look like? put it on a graph, well, it looks like this. There's all the points. Okay, so all the values, all the outputs were 3 less than the original table. The graph is still symmetrical in nature, but its vertex is at 0, -3. This can also be called the minimum or the turning point. Where does the graph cut the x-axis? You can see it here with the green arrows. Okay, they are equal to plus √3 and minus √3. √3 is 1.7 something. Okay, I'll show you how to get that in a moment. And you can see that this graph does cut the x-axis. It does go down below the x-axis, and there are 2 different places where it cuts the x-axis. Now, how would you do that algebraically? Well, your function x squared minus 3, when is it equal to 0? So when is it on the x-axis? So if we try to solve for x, we add 3 to both sides and we get a plus 3 on the right, and get the square root of both sides. What's the square root of 3? And there is 2 possibilities. It can be plus √3 or minus √3. Okay, and that's where we get 2 different real roots. Where does it cross the y-axis? Well, you can see down there at -3, the y-intercept is equal to -3, and this graph seems to have shifted 3 units down from the original plane x squared one. Okay, so we'll compare those. Okay, so comparing those quadratic functions, the quadratic functions describe a U-shaped curve. They have an x squared term, for example, and this is the what we just looked at, f of x equals x squared plus c. From the previous examples, we can see that the constant term, which is c here, okay, told us where the curve crosses the y-axis. Okay, so here's the 3 that we looked at, and the green function here, well, firstly the red function was just plain old x squared, okay, plus 0 if you like, and it crossed the y-axis at 0, 0. Okay, and it's symmetrical about the y-axis. Alright, the second one we looked at here, the blue one, is x squared plus 1, and its vertex and where it crossed the y-axis here was at y equals 1, and the green one was x squared minus 3, so it was the original red function but shifted down 3 spaces. Okay, so if you see something like this, x squared plus c, you can identify it on a graph by where it cuts the y-axis. You look for the c. Okay, now a little bit different. Okay, this time we're asked to graph the function f of x equals x plus 2 to be squared. Okay, now if you multiply that out, if you take x plus 2 multiplied by x plus 2, that's the squaring the bracket, you'd get this. Okay, it might be more familiar to you. X squared plus 4x plus 4. We've done these with quadratic equations. It's called a quadratic trinomial. Alright, there's 3 parts. There's your domain and there's the table. Use the calculator if we need to. So let's just look for a couple of inputs. When the input is -5, in the bracket you have -5 plus 2. Now that comes to -3. When you square it you get 9. Okay, and so on down the table. Okay, and use your calculator, it's quicker if you can. So here's our graph for that function, and here's our points using the inputs and outputs. Okay, so it looks like before. The graph is symmetrical, but the vertex this time is at -2, 0, so it seems to have moved the whole graph left by 2 units. Okay, there's our vertex, also called the minimum or the turning point. Where does the graph cut the x-axis? Well, it just touches it at -2. Okay, so a quadratic function, generally if it crosses the x-axis fully, okay, you'll have two different roots. Okay, and when you move the graph up a little bit so that it's just touching at the vertex, it's as if those two roots have come together. Okay, so when it's just touching the x-axis, we see it is at -2. We say that it has two identical real roots, that the two roots are the same, basically. Okay, and we can get that algebraically. If you remember, we had x plus 2 squared equals 0. We also had the expanded version, x squared plus 4x plus 4 equals 0. And both of those would give us this. If we factorize like we did when we did quadratic equations, if you factorize the expanded version, you're going to get x plus 2 by x plus 2, which is of course x plus 2 squared. And then the method to solve quadratic equations was to put each factor equal to 0. So you're saying, when is the function 0? When does it touch the x-axis? And we would solve for x by taking 2 from both sides. It's the same here. So there are our two identical roots of -2. Okay, where does this graph cut the y-axis? I can see it here at y is 4, or f of x equals to 4. All right. It crosses the y-axis at y equals 4, and this is known as the y-intercept. Okay, now algebraically you can see that best with the expanded version. Okay, so the function, when you expanded or multiplied the brackets, was x squared plus 4x plus 4. So to get your y-intercept, the x value for anything on the y-axis is 0. So you're going to calculate f of 0, and you get 0 squared plus 4 times 0 plus 4 equals, well, 0 plus 0 plus 4 is 4. There's your y-intercept. So in future now we'll keep an eye out for that, and it is the constant part here at the end, the part with no x involved, that will give you your y-intercept. Okay, and all in all, this graph seems to have shifted 2 units left when our function was x plus 2 to be squared. Okay, 2 units left. So this plus 2 in here gave the result to shift it left by 2. Okay, what happens when we have a different number in the bracket there? In this case, we have x minus 3. So we'll see what effect this has on the graph. Okay, on the previous slide we mentioned for the expanded value that we have useful information here, which is the constant part. This should give me my y-intercept, because when x is 0, we'll have 0 minus 0 plus 9. That will give me my y-intercept. Again, you should be practiced now at using your calculator to generate the outputs, so keep practicing that. And let's look at the graph of this function. Okay, so here are the outputs plotted. Again, you see it's symmetrical in nature. And this time we have the vertex of the function is at 3, 0. Okay, so it seems to me that the function has shifted to the right by 3 units. Okay, so 1, 2, 3. All right, and that's the minimum or turning point. Where does the graph cut the x-axis? Again at 3. So there will be 2 identical real roots there at 3. Where does it cut the y-axis? Now remember what we mentioned before. We said it should be plus 9 because the expanded version was x squared minus 6x plus 9. Okay, so there we have it, and here's the y-intercept at 9, or f of x equals 9. And the graph seems to have shifted 3 units to the right when our function has the form of x minus 3 to be squared. Okay, so we had plus 2 went left 2 and minus 3 went right 3. Okay, so here we have a number of things going on. So here is f of x is equal to x minus 2 to be squared minus 1. Okay, and we have the expanded version. When you multiply out the bracket by itself and take into account the minus 1, that's what you get. Okay, so let's look at the information this gives you. Now, we have a minus 2 here. When we had minus 3, the graph went to the right. So I think this one will go right by 2. And when we had a factor of minus 1 before, the graph dropped by 1, so down 1. And other information we can get from the expanded version is this constant value here gives me the y-intercept. Okay, given our domain here, use your calculator to generate the outputs. And let's see, does our thinking match the graph on the next page? So right by 2 and down by 1, and the y-intercept is 3. So plotting that function, here's all the inputs versus their outputs. So again, it's symmetric in nature, and our vertex is at 2 minus 1. So there's our vertex, and we said right by 2. So from the central line, we're going right 2 spaces, and down 1. We came down 1 from 0, 0. Okay, so yeah, that's it. And we can also see, what will be noted in a moment, the other piece of information was that our y-intercept was at plus 3, which is there. Okay, so where does it cut the x-axis? Well, it crosses the x-axis at 1 and 3. 1 and 3. And they're known as our roots. Okay, and we have 2 different real roots. Okay, now how could we have gotten that algebraically? Well, we can use the expanded version. Well, the expanded version was x squared minus 4x plus 3. Okay, so what we can do is we can ask, when is the function equal to 0? When does it cross the y-axis or the x-axis? And we can solve it as a quadratic equation. So get our 2 factors. Okay, so our 2 factors, when you factorize this, and you can use whichever method you're used to, will be x squared is gotten by x. The 3 is gotten by 3 by 1. Now they have to multiply to give a positive 3. So they'll both be the same sign, but they have to go together to make minus 4. So it'll be minus 3 and minus 1. Okay, so there's my factorizing. The next step is to put each factor equal to 0, and we'll add 3 to both sides to solve here. So x equals 3 is one root, and we'll add 1 to each side here. We'll get x equals plus 1 for the second root, and we can see those on the graph. Where does the graph cut the x-axis? Well, or the y-axis, we already mentioned that at plus 3. That's the y-intercept. So the graph seems to have shifted 2 units right and 1 unit down, given our function x minus 2 to be squared minus 1. Okay, so here's a few to compare. So f of x, when f of x is x plus 2 to be squared plus 3, this gives the red graph on the graph paper there. It's telling me to go, my pen now, it's telling me to go 2 to the left, so plus means you go left, and 3 up. Okay, so that's 2 left and 3 up, and you get your vertex. Okay, that's the red graph. G of x then is the green graph, and it's telling me to go 1 to the right and 2 down. So minus in the bracket is 1 to the right and 2 down. Okay, and on the graph from 0, 0, if you go 1 right and 2 down, that's where we end up for g of x. This one was called f of x. And the third one, the blue graph, is called h of x. Okay, and it has x minus 3. So minus means you go to the right. So right 3 and plus 1 up 1. Okay, so 3 to the right up 1. And let's see, is that the case? 3 to the right up 1 gives me the vertex for h of x. So just by looking at the functions, we're able to gain enough information to locate them on the graph. Okay, so there's more. All right, a lot to take in. You may have to rewind and go back through bits. Okay, so graph the function 2x squared. Okay, so what's different here? Instead of x squared plus or minus something, we have a number multiplied by 2x squared. Okay, there's our domain, and here's the table. So we'll stop here a minute and look at this table. Okay, so when the input is minus 3, you have 2 times minus 3 squared. Remember BIMDAS, you have to do that squaring first. It'll be 2 times 9, and we get 18. Okay, and on the next level we'll have 2 times 4 is 8. So multiplying by a constant like that, what it does, it gives us much bigger values than we would have normally. Okay, let's see what it looks like on the graph. Okay, so we're starting with f of x is the black graph here. Okay, and there we see we're going to be comparing some graphs that all have vertex at 0, 0. All right, now we saw when you use 2x squared, so on this slide it's called g of x, and that's the red graph, that you get much higher values for the inputs. And what that looks like on the graph is that the numbers increase really quickly as you go up. So there's 1 squared is or 2 times 1 squared, so you get 2 here, and the red line, it climbs much more quickly. Okay, so it has the effect that the U-shaped graph is much narrower. So it's narrower than f of x. If we look at the green graph, h of x, that's 3x squared. Okay, and that's narrower again. So the values for your outputs in the table are much larger than the other ones. And what it looks like is it's much narrower. The numbers get bigger much more quickly. So that's narrower than both f of x and g of x. And the blue one then is the opposite. If you multiply by a number that is less than 1, smaller than 1, it has the effect that the outputs are less than those of just x squared. Okay, and what that means is that the line climbs much more slowly, and so it looks much wider or broader than the other ones. Okay, so now we're going to look at a couple of functions which have negative coefficients. So f of x is equal to minus x squared, and that's the black function we see here on the graph. Okay, and the effect that the minus has, okay, is that it turns it upside down. So if your input is minus 4, f of minus 4 will be minus from the function, and then your input is minus 4 to be squared. So it'll be minus plus 16, which is minus 16. So you can see that here. Oh, sorry, here. Okay, input is minus 4, output is minus 16. Okay, so it has the effect to turn the whole thing upside down. And it is now, instead of being U-shaped, it's hill-shaped. The red function on the graph here is g of x, and it's minus 2x squared. So the 2 still has the function to, or the, what it does, it makes it narrower. Okay, but the minus turns it upside down. So it's narrower, but hill-shaped. And the green function on the graph there is minus 3. It's narrower again, and the minus turns it upside down. And the blue function is p of x. Now it is multiplying by a value that's less than 1, so that makes it wider. But because of the negative, it's upside down also. Okay. So this final slide then just compares a whole pile of different functions. Okay. If your function looks like this is f of x in the red. Okay, let's apply what we've learned here. A plus in the bracket moves things to the left by 2 in this case, so left 2. Plus 3, the constant, moves everything up 3. And a multiplying factor of 2 makes it narrower. Okay, so I think I have that there. 2 to the left, up 3, and it's narrower than the regular x squared. So on the graph, if we start at 0, 0, we go 2 to the left, up 3, there's your vertex, and it's a narrow graph. Okay, the next one is g of x. Okay, and it has minus 1 in the bracket, so that's right 1. My constant is minus 2, so down 2. And it's multiplied by 3, so let's call that very narrow. So let's check that on our graph. I think I have those 3 things listed there. So if we go right 1 from 0, 0, and down 2, I get to my vertex, and the green function is very narrow compared to the others. And the last one is called h of x. Okay, if we look into the bracket, it's minus 3, which means we go right 3. It's plus 1, so we go up 1. And it's multiplied by a factor of 1/3, so it's going to be wider. It's going to be wider than the others. Okay, and let's check that. So we're going to the from 0, 0, right 3, that's to here, up 1, and that finds my vertex. And yes, the blue one is much wider than the others. So lots to take in there. Go back through it a few times if you need. Completed square form. So the functions on the previous slide were written in what's called a completed square form. So they looked like this: y equals a times x minus h to be squared plus k. And we saw how useful that was, how much information that gave us for sketching graphs. A lot of information can be taken from seeing the function in this form. So for example, the vertex or the turning point could be read immediately as being h comma k. So h appeared here in the bracket with x, and this gave you the position left or right of the vertex, and the constant k referred to the vertical position of the vertex, so up or down. The axis of symmetries for the function, so remember our quadratic function is U-shape, and it does have an axis of symmetry where left equals right, is given as the position when x is equal to h. Okay, it centers around that. And we saw that if a is positive, so if the number being multiplied by in front here, if it's positive, you get a U-shaped graph. And if a is negative, we get a hill-shaped graph. And also the value of that multiplier a, if a is greater than 1, or the absolute value of it is bigger than 1, then the graph will be narrow. And if the value of it is less than 1, the graph will be wide. So lots of information when a quadratic function is written in this form. So what we're going to look at next is when you're given quadratic equations in different forms, how can you write it as the complete square form to get all of that information? Okay, so we're going to take the quadratic function y equals x squared plus 8x plus 7. So this is how we typically see quadratic functions written in the textbooks. And we're asked to express it in the completed square form. So the higher level exam, sometimes you're asked explicitly to do this. And we're going to use the information from it to sketch. Now sketch means that you don't need every single point along the curve, you just need the key points. So we'll see that. Alright, so how can we change this, what I refer to going forward as the expanded form. Expanded because everything is multiplied out and then simplified. Okay, how can we change that to the completed square form? So, and this is the method I like to use, and it's a very graphical method where you can see what's happening. Okay, so we're going to take the terms that contain x and create a square. So the terms containing x are the x squared part and the plus 8x. They contain x, and we'll leave the constant part, we'll sort that out later. Okay, so 8 or x squared plus 8x. So graphically we're going to show those areas equivalent to x squared and 8x. Okay, so a square that has value of x squared is gotten by multiplying x by x, and length and width are the same, so we have a square shape. Okay, we're going to represent the 8x as a rectangle. Its value is 8x, and that's gotten by multiplying an 8 by an x. Okay, so we're using area to show us these. Alright, so follow on. So the next step is we're going to split that 8x rectangle in two. Alright, so half it down the middle, and half of 8 of course is 4x. So the area of the left hand side there will be 4x and 4x, so together making 8x. And let's see why we do that. So what we're going to do is reorientate those two rectangles, put them along the sides of the blue square, so that now the total length along the top is x plus 4, and the total length down the side is also x plus 4. What we're aiming towards is a square shape. Remember, it's called completing the square. Alright, so half the x value and put half of it on either side of the square. So we almost have a complete square. Okay, we've this shape here that is x plus 4 wide and x plus 4 in length or height. Okay, so how can we make the complete square? Well, we could if we included this additional green square here. Okay, so we'll include that, and what that makes, it makes a big square that's x plus 4 in width and x plus 4 in height, and has area x plus 4 squared. Okay, so the addition of the green square creates a complete square with area x plus 4 squared. But what is the area of the green square? So we need to know that because we'll have to take account for it. So this little square here is 4 wide and 4 high. So 4 by 4 is 16. It has area 16 square units. And we will need to account for this additional area by subtracting it from x plus 4 squared. And then we can say that our original two terms here with the x's, okay, is equal in area to x plus 4 squared minus 16. So the big square minus the little green square. Okay, so they are equal in area. So to summarize, we started with this function y equals x squared plus 8x plus 7, and we'll refer to that as the expanded form. Okay, through our study of areas, we found that we can write those first two terms, x squared plus 8x, we can replace them with this expression, x plus 4 to be squared minus 16. Okay, so that's replacing those two parts. We still have a constant part of plus 7 from here. Okay, so here you can see that left equals right. Okay, the last step we're going to do is we're going to simplify the expression by adding those two constant parts. And so you get y equals x plus 4 to be squared minus 9. Because minus 16 plus 7 is minus 9. And now we've converted it to the completed square form. Okay, so this is what we wanted because it gives us lots of information. So for our sketch of this function, what information does it give us? Well, firstly, we can say straight away that the vertex is minus h, so minus this value, and the y value is that. So it's minus 4 comma minus 9. Say that straight away from just looking. The graph is U-shaped because it's leading with a positive x squared. From the expanded version we have the y-intercept, that's here. Y-intercept is plus 7. And if you wanted to factorize and solve the expanded form, you would get roots are minus 7 and minus 1. Okay, you can pause there and try that out for yourself. So heaps of information, from, especially when you use the two forms together. Okay, it's a U-shaped graph. The vertex is minus 4, minus 9. That's down at the bottom there. The y-intercept is at plus 7. See that at the second point there, and our roots, which we're able to get easily enough as well, are at minus 7 and minus 1, and so therefore we're able to sketch the graph quite easily. Okay, let's practice that by doing another one. Alright, express the quadratic function y equals 7 minus 6x minus x squared in the completed square form and use it to sketch the function. Okay, so first off, what I see here is we've got a negative x squared. Okay, so first we're going to factorize by minus 1 so that we have positive x values. So what's that mean? It means I take out the negative sign. I can put a 1 there as a factor if it helps me. So minus 1, and I've got 6x plus x squared in the bracket, and this is what I'm going to use in the little area map to make my complete square. Okay, so we've got x by x gives me the blue square. Okay, so I would have started with that. X by x gives x squared, and then the 6x would be 6 by x gives me 6x, and notice we've jumped a little bit ahead. We split it in half, gives 3 here and 3, and those yellow rectangles are placed along the sides. And to complete the square, we've got this additional area here in green, and of course 3 by 3 will give us an area of 9. Okay, that's the square completed. So that was all the previous steps all done together there. Okay, so we can replace this bracket here with the expression x plus 3 to be squared minus 9. So that was the green square there. Okay, so it's all replaced. What's left to do there is just to remove the square brackets, leaving the minus in front of the x plus 3 to be squared. Minus 9 becomes plus 9, and we've just rearranged so that we have the constants beside each other so that we can now add them, and I get minus x plus 3 squared plus 16. Okay, so now we're in completed square form. Let's use that to get lots of information for a sketch. Okay, so for the sketch, what can we say? Well, the vertex is at minus 3, 16. So minus whatever's in the bracket and whatever you have as the constant there. The graph will be hill-shaped because we have a negative a. Okay, a negative number in front. From the original expanded form, we have the y-intercept as the constant part here is plus 7. And if, okay, so there we go. So what did we get? We got our vertex at minus 3, 16. We know that it's hill-shaped, and my y-intercept is there at plus 7. Okay, so you can do a sketch. Now the word sketch means that it doesn't have to be 100% accurate, you just need the key points. Okay, so one more example to cement that idea, and also because there's a slight difference. Express the quadratic function y equals 3x squared minus 12x plus 10 in the completed square form and use it to sketch the function. Okay, so the difference here is that we have a coefficient beside the x squared part, and that coefficient is not a square number. Okay, so to deal with that, we will factorize our two terms containing x by 3. Okay, which is convenient in that 3 is a common factor there with the 12 as well. Okay, so first factorize by 3 so that we have a coefficient of 1. Okay, so that's taking 3 outside a bracket, and we've got x squared minus 4x plus 10. Now here's our area model. Again, we've skipped to the last part. What did we do there? We took what's inside the round bracket here. The blue area is x by x, giving us x squared. The yellow areas combined would have started as minus 4 by x, and we split it in 2 equal parts, so we get minus 2 and minus 2, and realign them. And then we had to add in this extra green area to complete our square. And so what have we achieved? We've achieved a full square there that has an area of x minus 2 squared, but we've learned that we'll have to account for this extra green area by taking away the 4. Okay, 4 was gotten, of course, by multiplying minus 2 in width by minus 2 in length. Okay, so we've done that here. Alright, replacing our original x squared minus 4x with x minus 2 to be squared minus 4. And what we're going to do now is to multiply back in the 3 to remove the square brackets. Leave the 3 in front of your x minus 2 bracket. 3 times minus 4 gave the minus 12. And we'll finish by just simplifying the constants by adding them. And we get 3 by x minus 2 squared minus 2. Okay, and now we've learned that we can take lots of information from this. So for the sketch, we can see from this value in the bracket and this value as a constant that the vertex is 2, minus 2. We also know because the 3 is positive, it's going to be a U-shaped graph. We can tell from the expanded version that the y-intercept is going to be plus 10. And also by the value of 3, I know this graph is going to be quite narrow, okay? And that's what we get there. So for the sketching, I would have first marked the vertex. Oh, there's the y-intercept actually came first there at 10, and the vertex is down at 2 minus 2, and we'd be able to sketch there a narrow U-shaped graph.